You press the accelerator, and the engine immediately pegs the red line. The tachometer spikes, but the digital speedometer beside it remains completely still. The vehicle has RPMs, but no forward kinetic transfer. Transmission slip is a universal diagnostic symptom, indicating a total loss of torque transfer. It represents the point where mechanical connection is replaced by internal sliding. In any automatic drivetrain, the engine and the wheels are not physically bolted together. The critical link transmine power is automatic transmission fluid. When that fluid fails, the resulting slippage manifests in divergent, catastrophic ways. The method of destruction depends entirely on the transmission's internal topology. To diagnose the failure correctly, we have to look past the engine flare and understand the structural differences inside the drivetrain architectures. Today, there are two dominant systems managing torque: continuous variable transmissions, or CVTs, and conventional automatic transmissions. This vector abstraction shows their core mechanical contrast. On the left, the CVT relies on macroscopic physical friction. On the right, the conventional automatic relies on microscopic hydraulic pressure. Torque routes through the left side exclusively via surface-to-surface contact. The CVT depends on maintaining precise friction coefficients between the belt and the metal pulleys. On the right side, the conventional automatic operates differently. It routes torque by using highly pressurized fluid to clamp down on clutches, locking specific planetary gear sets into place. Their baseline methods of moving torque rely on different physical principles, which forces their terminal failure modes into two distinct mechanical pathologies. Inside the CVT, the environment is mechanically straightforward. The system relies on two variable-width metal pulleys connected by a segmented steel push belt. To hold that segmented steel belt tightly against the smooth metal faces of the pulleys without slipping, the system requires immense clamping force. This creates a paradoxical requirement for the CVT fluid. It must lubricate the steel belt to prevent metal-on-metal wear, while simultaneously maintaining a specific friction coefficient so engine torque can transfer across the system. Heavy, sustained torque loads place extreme thermal constraints on this fluid. This graph plots fluid temperature against shear stability. As heat increases, it permanently degrades the fluid's chemical structure, causing the friction coefficient to drop below the transmission's operational limit. The moment the plot crosses that threshold, the torque load exceeds the fluid's remaining grip capacity. The belt begins to slide. Fluid breakdown here does not cause a gradual decline in performance. In a CVT architecture, it leads immediately to a catastrophic loss of mechanical grip. Without the necessary friction, the steel push belt loses traction, violently sliding against the smooth metal face of the pulley. This metal-on-metal slippage instantly generates extreme, localized flash heating. The intense heat and sliding friction inflict permanent structural damage, carving deep scars and gouges, known as scoring, into the previously pristine metal pulley face. Once the surface is scored, the required friction coefficient can never be re-established. It triggers a runaway feedback loop. The scarring causes exponentially more slip, which generates exponentially more heat. As the belt violently catches and releases on the freshly gouged metal, immense kinetic shock loads transfer directly into the thin steel tension bands holding the belt segments together. The tension bands cannot survive this erratic stress.
They ultimately succumb to the intense shock loads and violently snap apart. The core structural components are destroyed. This level of hardware damage requires a complete transmission replacement. CVT slip is a macro-level hardware destruction event, driven by a critical loss of friction. Returning to the conventional automatic transmission, we bypass the heavy planetary gears and look directly at a component called the valve body. This schematic maps the valve body, the hydraulic brain of the transmission. It is an intricate maze of microchannels responsible for directing pressurized fluid from a central pump out to specific gear nodes. If we follow a specific pressure path, we can see how localized hydraulic fluid clamps a wet clutch pack together, securely transferring torque through the gears. Without exact, sustained hydraulic pressure, that clutch pack will not clamp fully. The internal gear plates will slip and spin against each other. The ATF in a conventional automatic plays a distinctly different role than in a CVT. Here, it acts primarily as an incompressible hydraulic actuator rather than a surface friction modifier. An AT's ability to transfer torque is entirely dependent on maintaining unobstructed, highly precise microfluidic pressure gradients. Conventional ATs experience natural wear,
Over thousands of miles, the wet clutch plates shed microscopic fibrous material into the fluid. Fresh ATF safely suspends these particulates, but when the fluid thermally degrades, it loses its suspension properties. The debris coagulates into a dense, abrasive sludge. The transmission pumps this particulate-heavy sludge directly into the tight tolerances of the valve body's microchannels. This cross-section shows a shift solenoid attempting to slide open to regulate hydraulic pressure. The abrasive particulates wedge between the moving piston and the cylinder wall, halting its movement entirely. Because the seized solenoid cannot route the fluid correctly, there is an immediate pressure drop in the surrounding hydraulic channel. The resulting lack of pressure causes the corresponding clutch pack to slip. The friction burns the clutch material, shedding an entirely new wave of debris back into the system. AT slip is a micro-level hydraulic failure. It is effectively a localized stroke within the transmission's brain that paralyzes torque transfer. We return to the initial diagnostic symptom. The engine RPMs flare, but the vehicle does not accelerate. Side-by-side autopsies reveal their structural differences. On the left, the brute force destruction of a CVT. On the right, the microscopic blockage of an AT. One system failed because it could not maintain physical friction. The other failed because it could not maintain hydraulic pressure. Despite these architectural differences, the failures share an exact starting point. The terminal catalyst that initiates both failure cascades is chemically identical. The shared root cause is the thermal breakdown and particulate contamination of the automatic transmission fluid. Exceeding thermal limits destroys the fluid's chemical architecture. It eliminates the shear stability, keeping the CVT intact, and the suspension capability, keeping the AT clean. The transmission hardware rarely fails on its own. The fluid fails first, and the hardware simply suffers the consequences dictated by its architecture. For diagnosticians, this means slip is never an early warning sign. It is the final, irreversible manifestation of long-term fluid death. Torque transfer relies on the illusion of solid metal. In reality, it's only as robust as the thermal and chemical integrity